Everyone, it's really my pleasure um, to be here virtually meeting all of you and introduce you some of very recent work that our lab have on graph control barrier functions for large-scale multi-agent safe control. And so, uh, so what are barrier functions? Just in case that you have never heard about it, I plan to give a very short introduction of barrier functions and why it is a very powerful tool along with many other control certificate functions to help us construct control theoretical proofs for some system properties such as stability, safety, and being able to tracking some dynamic behaviors. So if you took some version of the control class before, you probably have learned this thing called Yaplon function. It is a pseudo energy function that people use to construct stability proof. Barrier function is very similar to Yaplon function, but it's not proving that a system will converge to an equivalent point, but instead that the system will stay in an invariant set. And if this invariant set happens to be the safe set that we care about, then we can use barrier function to prove that the system is safe. And of course, contraction metric is another form of the safety certificate that people use to talk about. But today, our discussion will be centered around barrier functions. And in my talk today, I plan to first tell you a little bit. It's a very mini lecture on what are control barrier functions and what are the challenges to use them. It's a very powerful tool, but still it is underused in many domains because it's very hard to synthesize or construct those functions for safety proof. And then I will tell you a relatively recent work, although this topic we have been explored very extensively, especially by my group at MIT, on how to use barrier functions for multi-agent systems. And we came up with a very novel idea of something called graph barrier function. I plan to tell you what are graph control barrier functions and how to synthesize them, how to use machine learning to get them, and use them for very large-scale complex multi-agent systems. And in the third part, I want to share with you an even newer result, very recent actually. It was presented at the International Conference of Learning and Representation just a couple of days ago on barrier functions blended into reinforcement learning. So if we do not have the model information or we want to use reinforcement learning for some of the very cool features, then we still a way to have barrier function and especially graph barrier function for multi-agent reinforcement learning. So I most likely won't have time to discuss this, but another interesting use of barrier function is to use them as safety filters. So here there are already some existing control policies that you have, and the barrier functions that we got from either synthesized by itself or synthesized using reinforcement learning, they can serve as a standalone safety filters. I know that I won't have time to go into this, but I'd be happy to point you to a few references that we have on this topic. So with that, let's get into the mini lecture of control barrier function. So if you have never heard about it, here is your first exposed to barrier function. And I hope that in the future, if you need to construct safety proofs or learn a safe controller, this barrier function will be a tool that you'll be able to use. So let's say we have a dynamical system. On this picture, it's this human being here. And in a classical setting, we assume that the system has a differential equation that is in a control affine format, in the sense that this controller is added linearly into the system, but there are nonlinear terms like this f and g, they could be nonlinear functions. So this is just a standard setup, and in the rest of the talk, we don't have to assume that the system is in a control affine term. It can be any nonlinear term, and it could be like unknown. We don't even know what these f and g's are. But for now, let's assume that we know the system dynamics, and it could be nonlinear, and it could be high dimensional. And I'm not trying to pose any other constraint, but I want to use this one-dimensional example to show you what is a control barrier function. Let's say we're playing a video game of controlling this person who needs to stay away from unsafe, which is a lava pool here. What we can do is just to control this person horizontally, control the velocity. So instead of controlling the position, you can think about like we can just control the speed of this person running towards or back from the lava pool. And this one-dimensional example, so we only have this position. The person is only able to move horizontally along this line. Now, what the barrier function is trying to do is it actually creates something called a barrier. It is a function that maps the state information into a scalar value. The scalar value is going to be positive for states that are safe, for states that are not the lava pool. And it's going to be negative for states that are unsafe. And the sign doesn't matter here. You will see cases when they flip the sign saying the safe is negative, unsafe is positive. It doesn't matter, right? Just flip the sign. And why is a control barrier function not a barrier function? Barrier is like positive for safe, negative for unsafe. That is a barrier function. Control barrier function tells us how to control the system to stay safe. And the way to do that is to find a controller. Remember, in this toy example, the controller is the velocity. So basically, control barrier function tells us the controller, which is allowed velocity, to make sure this agent stays safe. And the way to find this controller is by solving this last equation on the right corner, on the right bottom corner here. What it says is basically saying, I want to make sure that the derivative of h is positive at this line, which means that I want the h, because safe, when the system is safe, then h is positive. I want it to be always safe, meaning I want h to stay always positive. So this last equation here is telling us how we are finding the controller u to make sure this last equation satisfies. And if this last equation satisfied, then I can guarantee that h is always safe if it starts safe, meaning if it is going to be positive, always positive if it is start positive. Now, it's pretty easy to understand using this example that the allowed velocity is, of course, going to decrease when they are getting close to the lava pool, and it has to be zero when it's out of the barrier. And the further we are away from the lava pool, the more velocity we are allowed to have because we have some distance to make a stop. Right, this is just assuming there's a single integrator here as the underlying dynamics. So that is my mini lecture. Hopefully for now you understand what's the control barrier function. First, there's a barrier for safe and unsafe. Safe is positive, unsafe is negative, and control barrier function give us a way to find a controller to make sure h stays positive, meaning the system is always safe. So it's super intuitive and super simple. And there has been, I have to say, a lot of research on control barrier functions, looking at different types of systems, different degrees of freedom, how to construct them, and how to do them for multi-agent systems. However, most of existing work wants us to be able to write down a control barrier function by ourselves, or at least write down a parameterized version, so we can use some optimization tools like sum of squares to find those control barrier functions. So both these existing approaches are difficult because it's hard to find one or write down one or use sum of square methods to find a control barrier function for nonlinear systems and for systems with high dimensional dynamics. And it's also super hard to find one that the system have input constraints, meaning like previously, I didn't assume whether the velocity can have some sort of limitation or the if I'm going to control the acceleration, those are usually associated with the input constraints that we can have. So we only have limited. Usually we only have limited thrust for the systems. So the control CBF that we write down may say that you can stay safe if your system can run at a very high velocity, but in reality, our system may not be able to run at that high velocity. So whenever there is input constraint, it's super hard to construct a control barrier function to consider those. And it's also difficult to write down those for systems with complex safety constraints. Most of the safety people consider are distance-based. But let's say if the safety is like a conditioned on some other nonlinear terms, it's quite difficult to really write down this function. So all this adding together make it very difficult for engineers or for the users to really use barrier functions because we don't know how to get those. Now, for multi-agent systems, on top of these challenges I just mentioned, there are also a dilemma of what type of CBF to use for multi-agent systems. Of course, we can construct a big one, centralized one, but we know it's not going to scale. If we have like hundreds, thousands of these systems, then it's hard to imagine that one can write down or even to learn a CBF that is like tens of thousands of dimensions. It's not something that's realistic. But if we go with a decentralized version, these decentralized CBFs are always very conservative if you look at existing literature, meaning that they tend to stay very far away from each other. But if you dump a lot of agents in the environments, all of them want to stay far away from each other, meaning they cannot really move. So in a lot of the cases, the agents will just stay there, or they will not be able to really travel through narrow pathways or corridors to be able to, really get to their destination. And lastly, when previously in my mini lecture, you can see that to find the controller, we actually need to know the system dynamics. I was saying like you need F and G to be able to compute for that U. But if in many cases, especially nowadays when people are looking at different type of robotic systems, we cannot really write down a very precise model for those robots. There will be a simulation to reality gap. In a lot of cases, there are parts or components of the system that are unknown. So how can we even define a CBF when we do not have the dynamic information? So I plan to tell you a few recent developments that look at these different challenges by proposing a new CBF format for multi-agent systems that can scale and that is not conservative, and it will consider the input constraints and can be used for complex safety conditions. And lastly, if we do not have the model information, how to define a CBF and how to blend that CBF into the reinforcement learning process. So with that, I'd like to go to the first part of graph control barrier function for distributed safe control with input constraints and known dynamics. So for the first part, I'm going to assume that I know the dynamics. It could be nonlinear, it could be high dimensional, but I know that F and G function, or if it is not control affine, that's totally fine. I will know the dynamics. And the second part, I will move to the reinforcement learning part when we do not have the known dynamics. But they are all built on this very interesting idea called graph control barrier function, GCBF. So a very quick overview of GCBF, the problem setting. I'm looking at a multi-agent system starting with a very simple setup. So I have all these agents which are orange, and they have some sort of destination. I'm like, for now, I'm assuming that each agent's destination are given in the, like, you can see these green dots, and each of the agents, they are connected with their like destination. If they cannot reach there, you know that they haven't reached their destination. And now, on top of that, my multi-agent system have two types of like perception. The first is a local communication. So when the agents are close enough, they can form a line. You can see the very light gray or the black lines connecting them. But if the agents are far away, they do not really have that. That means when they are close, they can talk to each other, or at least they can see each other. And lastly, each agent has a LiDAR ray that's spinning around. This can be a camera, and we have versions that are exploring, but LiDAR could be a good starting point for understanding our environment, especially the obstacles. My agent doesn't really know where the obstacles are unless they kind of, I'm sorry, I see the video is a bit laggy for some reason, but hopefully you can see this tiny rays here for each agent. They will be able to have some LiDAR rays spinning around and detect the obstacles or each other if they are getting close. Okay, so what is a GCBF? GCBF is a fully distributed control certificate that can account for arbitrary and changing numbers of my neighborhood, and therefore it can be computed for a small-scale multi-agent system, but the same thing will generalize and work for arbitrary size multi-agent system. Arbitrary size doesn't really mean anything, but it can really generalize to a very large scale multi-agent system. And if we look at how it works, and this is just like a quick overview, you will see that each agent, actually the GCBF is defined per agent, and they will let me play this again. They will form this, like when I plot this heat map is the result, the value for the barrier function, and they will each have such one to make sure they are always safe in the sense that they stay away from the obstacles, they stay away from each other, and later I will tell you how they can also get to their goals while they are trying to stay away from each other. So now a little bit of mathematical definition here. Let's say we have a multi-agent system with n agents, and this n doesn't have to be fixed. It can be a changing number. It's naturally a graph. And in this graph, I'm considering two types of nodes or vertices. So my nodes or my vertices can be agents, and they can also be hitting points of the LiDAR array. So I'm not really distinguishing between an actual agent and something that my LiDAR array detects. So my LiDAR array, for example, in this setting, my algorithm wouldn't really know there's a surface here. All they know are there are some hitting points, meaning there is a point obstacle there. And maybe this point obstacles represent some sort of a shape that makes sense. Maybe it doesn't. It doesn't really matter here. And the edges are defined whenever two nodes or two vertices are close enough. So we define something called the sensing radius. When I have a sensing radius, I only care about my neighbors within the sensing radius. It could be, again, another agent. You can see that outside my sensing radius, I do not really care about this agent. So there's no edge between this, like agent 0 and agent 3 now. And I only care about the obstacles that are within my sensing radius. For example, the other surfaces of the obstacle, we do not really see them. Now, once we have the workspace, like it could be a 2D for the ground vehicle, 3D for the flying robots, high D for the manipulators. And if I have my sensing radius, and if I can define a safety radius, means like how far away means a system is safe, then we can compute something called the maximum number of my neighboring agents, right? For example, if my agent is here, in the middle, in the center with a sensing radius big R, and I can compute the maximum amount of agents around me that I have to care about. This is basically trying to define the largest input vector that I can take, because if more than that, some of the agents must be unsafe, or physically they just cannot squeeze in the space. But in my very toy example here, I can have at most 6 neighbors, including myself. That's 7. So 7 is a number of agents that I care about, and 7 multiply the dimension of each agent is the entire vector for each of my node that I will care about. So that if once we have that, what's the definition of GCBF? It is very similar to a traditional CBF with a few exceptions. So a GCBF is a continuously differentiable function h that takes in a vector of m. So this big M is a number of agents that I care about. And M is not just the dimension. M will multiply the exact dimension of each system. And this continuously differentiable function h is a GCBF if there exists an extended class kappa function alpha. If you do not know what is a class like K function, it is a function that's monotonically increasing. It has to be 0 at 0. And if I have this function and a control policy for each agent such that my derivative condition hold. This is almost the same derivative condition as what we have seen in the toy example. It basically says h dot plus alpha of this h is bigger or equal to 0, which basically says if my h was initially positive, and forget about the alpha term. If my h dot is always positive, then my h can only increase. So my h will always be positive. However, I do not want my h to be always increasing, which means I have to stay further and further away from unsafe. So this alpha term here basically says h dot has to be positive at the boundary. So at the boundary, you have to turn around. You have to stop and turn around. But if you're further away from the boundary, this alpha term here allow h to decrease, but still this together will make sure h is always positive if it start with positive. And this x here is basically the vector that containing all the information of myself and all the neighbors that I care about. Okay, so it's only the maximum number of agents I care about. It's possible that, I do not have that number of agents. I may have 0 neighbor, or may have 1 neighbor, or way smaller than m. It doesn't matter. It's this vector. You can just pad the rest of the elements of this vector to be, 0 or some number that you care about. And h dot itself is going to be computed using this Lie derivative of, it's very similar to a Liavan function to be the Lie derivative format. Now, this all sounds like a traditional CBF, but I have one more thing other than defining this h for each agent to be only on the state vector that containing itself and neighboring agents. We need the gradient of h to be 0 with respect to nodes that are far away, meaning for any agent, any of my neighbors outside my sensing radius, I do not care about them. And the way I do not care about them is that the gradient of h is going to be 0. That's how I do not really care about them. And that can make sure that we do not really have to be bothered by the agents that are further away. And of course, we need some sort of a smoothness to make sure there won't be jumps around the sensing radius. It cannot be like a huge gradient when it shows up in my sensing radius and 0 further away. So we need some smoothness here, and I will tell you how to get that smoothness. So basically, we have proved the theorem saying the existence of a GCBF it will guarantee the safety of an arbitrarily large multi-agent system from non-colliding initial condition. So this arbitrary thing is really important here for the generalizability perspective. Now, what he's saying here is, although I have a multi-agent system, all I need to do is to make sure each agent has my GCBF condition hold, and as long as each agent has this satisfied, overall, we can construct a safety proof for the entire multi-agent system, but I do not have to have that central CBF for the entire system. Okay, now, as I said, one critical part of GCBF to be true is that the gradient of h has to be 0 for agents that are far away, and you can imagine it need to be smaller and smaller when your neighbors get closer to the sensing radius. And one way to do it is to encode my h in this above formula, where we have psi1 and psi2 are two encoding functions, and this W is a continuously differentiable function that is 0 for agents that are away from each other. This may look a little bit of like strange, but actually this is a very natural way of encoding for h if we just use the graph attention idea. So graph attention is this idea in graph neural networks where we have this attention layer. It's not really the attention in the physical sense, but you can think of it as attention, like kind of like attention. You pay attention to your neighbors. When your neighbors are really far away, like are outside my sensing radius, my attention is not really having any attention to the agent. So that attention is 0. And the closer my neighbors to me, the more attention I will pay to them. And our contribution is really to represent both h, which is our GCBF, and the policy, which is another distributed policy, as graph neural networks, and find them using machine learning over GNNs. And how to do them? The whole learning process is quite straightforward. We encode both the h and the policy pi using GNNs with corresponding parameters for the weights and biases and other, important architectures. And we have this loss term called the loss for CBF. This is a loss for constructing the CBF condition. It has 3 terms, but it's quite easy to understand. I have some color encoding here, but let's just look at the first one. The first one is blue. What it says is, I really want my h dot plus alpha to be positive. So I will penalize it when this term is negative, right? So basically my last term will become 0 when it's positive, and it will give me a big loss when it is negative. And that's how the first term is constructed. And again, like this zi is here, there are input features to the GNN, and here it could encode both vertex and edge features. And these features, for the vertex features, it could encode the type of agent. It could be a same type of agent as me, or it could be a failed agent. It could be a malicious agent or adversarial agent. It could be a static agent that is an obstacle. So those are the features. You can give as many features as you want. And the edge features could be pretty much the thing you want to know about your neighbors, right? If it's a LiDAR hitting array, you want to know that where is that, our point obstacle? Where is that not LiDAR hitting array? And how long is it? What's the angle? If it's a neighboring agent, you want to see if that's an agent who want to share some information with you. Now, when you're close, you can exchange some information. Now, that's the first term. And what the rest two terms are basically saying that, remember, my H is positive for system that are for states that are safe, and they are negative for states that are unsafe. So basically, the second one says, if my data is unsafe, then I want H to be negative, and I will penalize it when it is positive. So this bracket parenthesis plus is a ReLU function. It will output the same value when it's positive, it outputs 0 when it's negative, right? So this will make sure, like, if H for unsafe is positive, there will be a loss term occurred. If it is negative, then this whole term will become 0. So I do not penalize it here. Similarly, for the safe parts, that means the control invariant set, meaning like the H can be, I have a controller to make sure H is positive. Then I will make sure H is positive in that region. Okay, so this is a very intuitive, a very straightforward lossless function, and this intuitive one actually works pretty well. Now, I mentioned input constraints to be able to account for the input constraints, meaning we have very limited amount of input thrust that our actuations that we can provide to the system. Then we add another loss term called the control loss. The control loss is basically trying to minimize the distance of my learned controller to a behavior cloning policy, where this behavior cloning policy can be from a nominal policy. It's basically any policy that you want to design for your system to execute some mission. And here we can also choose this behavior cloning policy to be a QP policy, which means this policy is computed by looking at the feasible actions admissible by the CBF that we learned by solving a quadratic programming. And this quadratic programming is pretty much the same quadratic programming that we have introduced in the toy example to find that U. So in this way, we can actually really respect the input constraints and reduce sensitivity to hyperparameters. For example, I have some illustration on the right. If we use the traditional arbitrary nominal policy, in this way, it's this agent is trying to get to the destination, which is a green dot across the obstacle. The nominal policies is a policy that points directly to the green. So you can imagine with getting close to the green, it will have to, like, you will have, like, the CBF will make sure the agent will have to stay away from it. Now, if we use the nominal policy here, that input constraint will have some issue here because we do not have arbitrarily large input actuation. Now, if we penalize too much on deviation from the nominal policy, and then you will see that the agent will try to follow the nominal policy and encounter unsafe behavior. However, if we give a small weight to, like, very small weight to the deviation from the nominal policy, then the agent will stop here because the nominal policy says you have to go toward the goal, but the control barrier function says you have to go the other way to stay away from the obstacle. Now your agent may have to stop here. With the right amount of weight, you might be able to find a correct policy that can still get to the goal and avoid obstacles. However, if we just directly use the QP policy as the nominal or as the behavior cloning policy, then this is really not sensitive to that weight. However, that weight you choose, the agent will still always be able to reach the destination and avoid the obstacles. So with all that, this gives us the entire architecture for learning a GCBF. Here, I'm showing you how the learned attention weight can automatically satisfy the GCBF condition. Remember, we want the attention to be more when your neighboring agents are close to you. So you can see when your distance are very small, there's a large attention. And this attention will get smaller and smaller when you are getting close to the sensing radius, and it will reduce to 0, and it will be complete 0 when other agents are outside your sensing radius. So that is exactly the condition that we want to learn. And the overall learning architecture is also pretty standard. We have some controller start as a starting point. We will collect trajectories and these sample input features. We'll label this data as unsafe or as safe or control invariant. This data will be sent to learn the GCBF through this loss of GCBF, the 3 terms I introduced, the very intuitive penalizing the violation of the GCBF conditions. At the same time, we will solve for a QP policy from this learned GCBF to give us this behavior cloning policy. The 2 loss functions together add them together to give us the entire loss we will be used to back propagate it to find the controller and the GCBF. Now, with all the math, let's look at the results. These results are trained with either 8 or 16 agents, depending on what's the maximum number of agents that you care about in your neighborhood. Then it can really generalize very well to a large scale. I'm plotting here with, I think, 500 agents, but in the paper, we can do this experiments all the way to 4,000 and go beyond. It really depends on how crowded the environment becomes. If the density of the agent is the same, then no matter how many more agents you add, this single controller trained with a small number of agents can work on all of them. But in the stress testing case, we can squeeze in more agents in a smaller environment. So that's the next one. You can see the same space, but more agents, and the agents will become very crowded. At some point, they need a longer time to figure out themselves outside of the entanglement here. So in this way, we can still scale very well to like 500. But if you're done more, you can start to see that the safety rate is still the same, but the agents will have to squeeze in some very crowded area and spend a long time to get out of the crowded area before they can move forward. And of course, these agents, they are trained without knowing the obstacles. I can throw some random numbers of obstacles in the environment, and the obstacles, I don't have the moving obstacles here, but the obstacles can definitely start to move. It cannot be too fast, but even if the obstacles are slowly moving, they work perfectly well. And in the training, we do not sample the obstacles. Instead, we directly sample some random hitting points. So in that way, the agents will learn to avoid any type of obstacles. So this thing is also learned very robust in the sense that we train everything in simulation, but test it directly on hardware using the crazy flies. So these crazy flies are palm-sized quadrotors, and we force them to fly on the same level, so they have only like 2D of freedom to move, and they need to avoid collision with each other and avoid collision to the static obstacles. Now here, the agents are trying to go to the opposite direction and form this sort of like a circle. In the next one, we can actually impose an intruder. So this intruder is an arbitrarily malicious agent that is trying to move around and perturb the formation. And you can see that it's actually a person holding this intruder, trying to get close to all these agents. Even with the intruder, the agents are able to still avoid collisions while being able to really get to their opposite direction and eventually form the circle that they initially would like to. Okay, so eventually when the intruder slowly start to move away, you can see how these agents finish their tasks. And we're being very malicious here. You're really trying to perturb the formation of the rest controlled agents. And we have a lot more other type of hardware demonstrations. They're all very cute to look at, and you can check out the website. And I have a QR code here for GCBF. It's called GCBF Plus because it's a journal version rather than the conference version. But everything I've talked about so far is contained in this website, and you can check it out. So without taking too much time, and by the way, we also built some simulation environments to test all these different types of robots conducting different type of missions and see how well the learned controllers are. And without spending too much time on these videos, I would like to quickly introduce to you the second part where we want to understand what will happen if we do not have the dynamics. So GCBF is great and it works, it generalizes very well. It gives us this rigorous safety proof if it's learned to be the correct one, and it will consider the input constraints. But in many cases, especially today when we do not have the dynamic information, how would we still find a GCBF? More importantly, this question is, how should we make autonomous multi-agent systems both smart and safe? For smart or for intelligent, this topic is often associated with reinforcement learning or multi-agent reinforcement learning. And for safety, it can be provided by CBF, as we just talked about. Previously, the way people put these two together is to use a CBF as a safety filter for multi-agent system. But again, you still need to write down your own CBF, or you may have to, or the CBF may not really work well in the sense that it can give you a very poor filter that filter out everything that reinforcement learning says. We want to have a very elegant way to blend these two together, and that is the thing I want to use around 10 minutes to quickly talk about, called DGPPO. It's called Discrete GCBF PPO for multi-agent safe optimal control. And this work, as I said, was presented just a few days ago at the iClear conference this year. So the setup is the following. We consider a multi-agent safe optimal control problem, thinking about a group of agents trying to push a very giant box into the destination, like some sort of warehouse. And the agents will together, what we need to do is we want to learn a policy. More importantly, because we want to scale well, we want to learn a distributed policy. Although there's a single objective for example, to push the box, which means we have one global cost. The cost is defined globally, not for each agent, but we want a policy to be distributed. How would the agents work together to distributedly, but for one central objective? And secondly, the agent needs to have only local observation. So which means the same thing. We have a sensing radius. The agent can only see what's around them. And when it's outside their sensing radius or when things are blocked, we'll see one example. For example, the green robot here probably is going to be blocked by the box. So the blue one won't be able to see it. So there's only local observation. And at the same time, we want all sys agents to be safe. None of them should bump to the obstacles or violate other safety constraints. And finally, we have some unknown dynamics. Here, I'm assuming the dynamics are discrete only because, in RL, mostly people assume discrete dynamics, but this can be continuous. And it doesn't really matter. The math works pretty much the similar way. And even if you're looking at a continuous dynamics, when you implement it, you can still implement it in a discrete way. Okay, now, and for example, if we want to use a humanoid, it's very difficult to write down the F function for a humanoid robot. How would we deal with this unknown dynamics? So this is my basic mathematical setting. Here, for the global minimizing the global cost with local observation and unknown dynamics is probably most likely going to be something that only RL can solve. And for only local observation and safety, this is something from my introduction of GCBF. You probably can believe that GCBF will be able to solve. Now, the question is, how would we blend these two things together in a non-trivial way, instead not just applying GCBF on the policy that RL learns? And in most cases, what I will show you that it's not going to work. Okay, so come back to GCBF. Remember, GCBF support local observation and it can make sure systems are safe. However, we actually do not have we need a known policy as a nominal policy, right? So in my previous setting, the agent has a destination to go, and that destination is given. But here, we actually do not have that given destination or given nominal policy. GCBF would assume a known policy that is performing the task. It only guarantees safety and make sure the policies are safe, but they cannot really help you solve the task. And GCBF will assume known dynamics. Now, to solve the first problem, I'm going to tell you how to extend GCBF to unknown dynamics. And that known performance policy will be given by RL, and we'll get to it very, very quickly. So remember, GCBF is a CBF for continuous time, partially observable multi-agent system, assuming known dynamics. The key insight here that we use in this work is to prove you that a constraint value function itself is already a valid GCBF for the discrete time, partially observable multi-agent systems. So there is a long proof that you can check out in the paper, but here, the good news is that instead of learning a GCBF from the sample points using that lost function to penalize the violation of the conditions, I can prove to you that the constraint value function, which is taking the maximum of all the infinite horizon safety for where H defines the safety constraints. So one thing, sorry, I didn't mention here is, let's come back here. So staying safe means that my safety constraint is described using the H function, which is given as a safety condition. If I take the maximum of H over infinite horizon itself, I can prove it already satisfies the three conditions that CBF would need. So it's this constraint value function itself is a valid GCBF. Now we know that if we manage to learn this constraint value functions through any off-the-shelf methods, then we'll be able to already get a valid GCBF. So from the agents, we will collect some deterministic rollouts using these deterministic rollouts to learn the constraint value function. So that's step number one. Now, we still have the problem, how to get a policy that actually finish the task. Remember, GCBF makes sure agents won't bump to the obstacles, but it won't push the box for you. Some policy will need to be learned to push the box. And without the safety part, the rest seems to be a problem that is a traditional multi-agent reinforcement learning. Global cost, local observation, unknown dynamics, and we can use MARL, specifically MAPPO method to learn such a policy. Now, the way is also quite standard. From the policy, we get some stochastic rollouts. Using these stochastic rollouts, we'll be able to learn the performance value function. Now here, it is the value function corresponding to the cost function that we have. Using that, we get the value function, which will be able to give us a policy that using PPO loss will be able to learn such a policy for the objective. Now, next thing is I have two things, MAPPO to get me a policy for the task, GCBF to get me a policy for safety. How can I get one policy that perform the task and guarantee safety? And the way to put them together is basically this idea of DGPPO, where we actually will use the constraint value function, which is our valid GCBF here to do what we call the gradient projection. So the idea is if the current policy already satisfies the safety constraint, then this gradient will take one step to minimize the cost of the objective. However, if the current policy already violates the safety constraint, the gradient of the policy's gradient will be projected using my GCBF to take one step to maximize the safety instead of the objective. So in this way, it can really nicely the same rollout. We will have two types of rollouts: stochastic ones for learning the regular value function, and deterministic rollouts to give us the GCBF, and we actually reuse the stochastic rollouts here as well, just to be more data efficient. And together, this is the DGPPO framework that give us a policy that can really perform the task and at the same time guarantee safety. And this is not only for safety. You can pretty much use this idea for any constraint optimal control problem where any violation of my constraint can be considered as a violation of the safety. It doesn't have to be the actual physical safety constraint. And my objective now can be very general. It could be any high-level objective. I'm giving you a quick few examples here. For example, I want all my agents to move around, avoid obstacles, but form a line on the left. Or multiple agents are pushing this box to make sure that the middle of the box will never collide with these random sampled obstacles in the environment. So those are central objectives. So here, the objective is to form a line or to push this one box. It's not separate anymore, but the agents, they only have local observation, and they will be fully distributed when they are being executed. There are many more other tasks that we have tested, and I can show you the numerical results. So remember, what we want to get is the best trade-off between safety and performance. There are many methods, for example, penalty-based methods. You can penalize safety. That is basically a lot of the safe RL work is doing. You just penalize it when safety is violated. Of course, when you penalize it, it's basically like very similar to the Lagrangian-based type of ideas. You have to play with that parameter because now we are facing a multi-objective, safety and performance. To balance those, either to penalize it or to use the Lagrangian method, we have to choose the weight. And we can show you that the weight really play a big role here in the sense that the performance is very sensitive to the weights. So you can see there is a strugglement. Some of them have a good safety rate, but they are very bad in terms of the performance that give us a very high cost. Others are good at cost. For example, if you really forget about the penalty on safety, you can get a good performance, but the safety is going to be violated a lot. So of all the environments and all the methods that we looked at, DGPPO here really achieve the best performance of all the policies that are safe, and is the safest policy of all the results that are performing well. So it really gives us this best trade-off. And of course, this is a multi-objective optimal control problem. There will be trade-offs you have to make, right? Which means to account for safety, we have a pretty good safety rate here, very close to 100%. The performance will have to degrade a little bit because you have to sacrifice some sort of a performance to make sure all agents are safe. And I also have some interesting hardware experiments. In this setting, what the agents are doing are these two agents in blue, they are two surveillance agents that has a camera in front of them. And the gray zone is the zone that they can really see the target that they are tracking. Now, the goal for these two agents are to make sure that they can always keep the target within their range of sight. So this yellow one, which will turn green if they are being observed, they should stay in at least one of these gray zones, and the boxes will block the camera. So in that sense, you can see when one agent starts to approach and observe the target, this target will turn green. Now the target is moving around. When the observation of the left agent being blocked by the boxes, the other one learned to catch up and really take on that job. And they two really cooperate very well to make sure at least one of the agents keeps seeing the target that is being observed. So the target being observed is the central objective, and these two agents operate in the distributed way. Of course, they also need to make sure like they don't bump to the target and they don't bump to the static obstacles. I have results for other baselines, but I probably won't have time to go through those. And another example is very standard. All these agents need to get through the corridor. We do not give them the order. We do not give them the path, and they will figure out what's the best way to fly from one side of the corridor to the other side. Okay, so that's pretty much like, as I said, I know I'm not going to have time to talk about the safety filters, but be happy to point you to some results that we have if you have interest. Let me quickly summarize here. So in today's talk, I introduced the control barrier functions as a very powerful tool to synthesize safe controllers. However, they are very difficult to get. You have to be trained to be an expert to handcraft one, even for simple systems. For systems with nonlinear dynamics, with high dimensional dynamics, and with input constraints, it's really hard, if not impossible, to find a CBF for them. However, the good news is we can learn such CBF. For multi-agent systems, we have introduced this idea of GCBF to help us synthesize fully distributed, decentralized, scalable, and generalizable collision avoidance safe controller. And these GCBF and policies are both learned as GNNs. And then in the second part, I introduced that constraint value function itself are valid GCBFs. So in this way, it's very good for us to just use the constraint value function within the multi-agent reinforcement learning or simple RL setting. It is also okay. So we can use constraint value function in the RL setting, so we can get a good performing policy that is also safe. And the three papers, the two papers I covered today are the GCBF paper that was eventually published at the Transaction of Robotics this year, and also the iClear work. So for the safety filter work that I didn't get a chance to introduce today, we have an ICRA paper last year called How to Train Your Neural Control Barrier Function. This one talks about the idea of using the barrier function as a standalone safety filter. And if you have questions, I'd be happy to discuss those.